nanoHUB-U, online instruction.
Welcome back to Unit 2 of our course. This is the 4th lecture. Now, what we did in the last lecture was to develop this quantum model, which includes inflow and outflow. So, at the level of the Schrodinger equation, you have these additional terms, the sigmas and the s's. And what we showed was they give rise to these inflow, that's S1 dagger A S1, S2 dagger A S2, and the outflow, the psi dagger gamma psi, psi dagger gamma 2 psi. And this gamma is this anti-Hermitian part of sigma. A, that's like a density of states related to the Green's function. So these were all the concepts that we introduced in the last lecture. And in this lecture, what we want to do is put it in the form of the regular NEGF equations, which will be the standard form that we'll be using and referring to later. But before we get started, just wanted to remind you of something I mentioned in the introduction, and that is that when you look at this number of electrons, I said you could look at psi dagger psi. And psi is, let's say, a column vector with 3 components. If you, let's say, had a lattice with 3. I mean, in practice, of course, it may be 10 or 100 or 1000. But to illustrate the point, just think of a lattice with 3 points. And then psi has 3 components. And the psi dagger is, again, those 3 things, conjugate, and it's transposed. So it's a row vector. Now, when you multiply the two, what you get is 1 by 3 times 3 by 1. Of course, for matrix multiplication, those 2 terms must match. And what you get is a 1 by 1, which means you just get a number when you multiply the 2. Now, you'll notice here we have psi dagger gamma psi. The gamma is a matrix. But the psi dagger gamma psi, that when you put in a gamma in the middle, well, you're putting in a 3 by 3 here. That's fine. But when you multiply it, you still get 1 by 1. So the point is that's still a number. Single number, a 1 by 1, when you multiply it all out. Now, on the other hand, if you look at psi dagger, then the order is reversed. And now when you multiply it, it's 3 by 1 times 1 by 3. And so what you get is a 3 by 3 matrix, which we call Gn. And I guess the 2 pi, I'll say a couple of words about it later. But basically, this Gn is like the matrix version of the number of electrons. And here, I guess I get one number, which is like the number of electrons. Here I get a matrix, but if I add up the terms on the diagonal, then I'll get the number. So the number of electrons is like the trace of this matrix. Another matrix we'll use in the NEGF equations is the similar quantity, but related to the source term S. So SS dagger is what we'll call sigma n over 2 pi. And that again will be a 3 by 3 matrix in a problem like this. Okay. Now let's look at our expression for current. As we said, if you looked at contact 1, you have an inflow and an outflow. So if you write it out, the current will be, this is the inflow, that's the outflow. And each one of these is actually a number, as we just discussed. So if it's a number, I could always call it the trace. Of course, usually trace means you add up all the diagonal elements. But if you have just a 1 by 1 matrix, which is a number, then the trace is basically that number itself. So this is a number and I could write it as trace. Of course, it kind of looks silly why I'm calling it a trace, but you'll see that in a minute. But let's do that. And then I know this rule that once I have traces, when I'm taking a trace, I can always move these things around as long as I preserve the cyclic order. So what I could do is, here, the psi dagger, instead of being up front here, I could put it at the end. So you'd have a psi dagger there. Similarly here, S1 dagger, instead of being here, I could move it there. Now, notice that now the trace actually makes sense. What I mean is, if you think about it, if the psi was a 3 by 1 column vector, then this is actually a 3 by 3 matrix, that's a 3 by 3 matrix. So the thing we have here is actually a 3 by 3 matrix. And so it makes sense to take its trace. See, here as I said it was a number, the trace was kind of a cosmetic thing that almost looks silly. But the reason I did that was so I could move it around. And once you have that, you see, I could replace psi dagger with Gn over 2 pi, SS dagger with sigma n over 2 pi. What happened to the 2 pi? Well, I had this h bar down here. 2 pi h bar is h. So now it has become h over here. And the other thing to note is that this quantity here is like the flow of electrons per second. But if you actually want charge current or coulombs per second, then you need to multiply by the Q as I have done here. So that's this expression for the current. So now you see from this picture that we had from the last lecture, I could turn it around and write it like this. You have this channel inside which you have Gn, which is the matrix representing the number of electrons. I have A, which is the matrix representing the density of states. And the rate at which things come in depends on the trace of the sigma n times A. The outflow is the trace of gamma times Gn. So physically, these quantities are just like what appear in our semi-classical model. And you can see the correspondence. You see, A is like density of states. Gn is like number of electrons. The gamma is like the nu, this outflow. And the capital S, this inflow, is like the sigma n. So this picture is important to keep in your mind because as we do these NEGF equations, there will be so many symbols that unless you have a good physical picture, it's hard to keep track of them. Okay? So that's why I spend so much time trying to get just this physical picture in terms of inflow and outflow clear. Okay. Now, the next thing that you wanted to show quickly is that, I said that Gn is like n and A is like density of states. So what you might expect is, if I take the trace of Gn, that will tell me the number of electrons per unit energy in a given energy range. And if I integrate it over energy, then I should get the total number of electrons. And that you might expect based on psi dagger. And this 2 pi part of it kind of comes from this Fourier transform type of relationship. Namely, you see, if you had a psi in time squared integral, there's this Parseval's theorem that you see in quantum mechanics, energy and time are like Fourier transform variables. So when you go from one to the other, there is this Parseval's theorem, as I said, which relates the integral dt psi t square to integral dE psi e square. And there's usually that 2 pi. So that's kind of the origin of the 2 pi there. Doesn't matter too much, as you'll see. It kind of cancels out. But you have to remember, when trying to find the number of electrons from Gn, you have to remember to divide by 2 pi. Now, similarly, when you look at density of states, you expect the same thing, that you have A and you integrate the trace over all energy. And A, of course, we defined as Gr minus Ga. So it looks like that. But what it should be equal to is the total number of states. That means if I had started from a H matrix that, let's say, was 100 by 100, then as you know, we'd say it has 100 eigenvalues. There are 100 states. And after adding all these sigmas and everything else, when we calculate A and you take the trace, integrate over energy, the point is the answer should be 100. See? And that's not obvious at all, but you can show it, but I won't go into it in the lecture. But the main thing then to keep in mind as you try to navigate through all these symbols is that this A is like density of states, Gn is like number of electrons. Gamma is the rate at which things leak out, and sigma n is the rate at which things the source terms that electrons want to come in. Okay. Now, once you have that picture, you'll remember from our lecture 2 on semi-classical model, I argued that there has to be a basic relationship between S and nu. You see the S that comes in and the nu that tells you the rate at which they flow out. If one is big, the other must be big also. If it's easy to flow out, it must be easy to flow in. And the way we argued is, think of a special situation where you have only one contact connected. And in that case, the number of electrons to the number of states ratio must be equal to the Fermi function in the contact. That's the basic law of equilibrium statistical mechanics, that if in your contact in a certain energy range, let's say 50% of the states are occupied, and then if you have a channel come in contact with that, at equilibrium, in the channel also states will only be 50% occupied. So that requirement kind of leads to this relation between S1 and nu1. And from the analogy, you'd say, well, that suggests that the sigma n in our quantum picture from contact 1 should be gamma 1 times F1. Similarly, for contact 2, sigma n2 should be gamma 2 times F2. Now, we can move on to the NEGF, basic NEGF equation that I think we had discussed in the introduction, that what we want to do is start from the basic, this modified Schrodinger equation in terms of psi and s, and try to get the NEGF equation in terms of psi dagger and ss dagger. That is in terms of Gn and sigma n. And the way you do that is, first you take this, invert it to write psi as Green's function times s. So that psi dagger is s dagger times the advanced Green's function. I see the retarded Green's function is defined here. Advanced one is its conjugate transpose. So then when you put in, look at psi dagger, you get GRS and then S1 dagger GA. This is what you call Gn over 2 pi. This is what you call sigma n over 2 pi. You'll notice the 2 pi's just cancel out. So you get the this NEGF equation, which relates the psi dagger to the SS dagger. The important thing is that in the Schrodinger equation, it would be kind of tricky if you put in two sources, because then you'd be getting interference between those sources. But in the NEGF equation here, you can add sources. So you could say, what is sigma n if you have multiple sources? Well, just take the sigma n due to contact 1, sigma n due to contact 2, add them up. And as we just discussed, this one is gamma times f, gamma 1 f1, that's gamma 2 f2. Now, one interesting check to make, and this gives us a very important identity that you should be familiar with, it's that supposing, you see, these are general equations under non-equilibrium conditions. But supposing we had an equilibrium situation, which means the two contacts had exactly the same Fermi function. F1 and F2 both equal to F0. Well, in that case, sigma n would be gamma 1 plus gamma 2 times F0. And the sum of the two, that's what we have called gamma. So at equilibrium, this is gamma times F0. Well, let's put that into this equation. So you'll get GR gamma GA times F0. Remember, these are all matrices, whereas F0 is just the Fermi function. It's a function of energy. So at a given energy, it's just a number, 0.5, 0.4, whatever it is. Whereas these things are all matrices. Now, the point is that at equilibrium, of course, what we expect is that the number of electrons should be equal to the density of states times the Fermi function. That, as I mentioned, is this basic law of equilibrium statistical mechanics. That if you have a channel in equilibrium with a contact, then in a given energy range, the fractional states that are occupied, the fraction of states that are occupied must be the same. So what should happen is, this should be equal to A times F0. But the question is that true? Is A equal to GR gamma GA? Well, it's not obvious that this is guaranteed, because the way we defined A was I GR minus GA. That doesn't look the same as that. What I'll show next with a little algebra is that this is indeed identically equal to that. So how do we show that? Well, first thing is we start from the definition of GR. We take the inverse of both sides. So we can write GR inverse is EI minus H minus sigma. Next, we take the conjugate transpose of GR inverse, which is EI minus H minus sigma dagger, because here also we are taking the conjugate transpose. I remains I, H is Hermitian, so it remains H, but sigma becomes sigma dagger. And the point to note is that here it's inverse and then dagger, but in matrix algebra, you have probably seen, if not, you can work it out, that instead of inverse and dagger, you could reverse the order. You could have the dagger and then the inverse. And then the GR dagger would be GA inverse. So GA inverse is equal to that. Next, what we can do is subtract from here this one. So GA inverse minus GR inverse is equal to this minus this, which is sigma minus sigma dagger. And as you remember, if you remember, we had the definition of gamma as I times sigma minus sigma dagger. So sigma minus sigma dagger is minus I gamma. Now what you can do is multiply from the left with GR and multiply from the right with GA. So you have GA inverse. When you multiply from the right with GA, it goes away, and then you becomes identity, and then you multiply by GR, so you get GR. The second term, the GR inverse is just identity, and multiplied by GA becomes this GA. And here you have minus I gamma, and you have the GR on the left, GA on the right. So you have this expression, and that then leads to this expression for A. A is I times GR minus GA. When you multiply by I, the minus I drops out, so you get GR gamma GA. And interestingly, it's GR gamma GA, but it could have been GA gamma GR just as well. Because instead of multiplying from the left with GR and from the right with GA, I could have done just the reverse. I could have multiplied from the left with GA and right with GR, and then I'd have got that. So that's just for completeness, that this is an identity that is often very handy. But in this context, of course, the main reason I was doing it was to show that the NEGF equation does give you the correct equilibrium result when all the Fermi functions are the same, because GR gamma GA is indeed equal to A. So when you apply it to an equilibrium problem, it gives you the expected results that the number operator here, the Gn, the matrix that represents the number, is equal to the matrix that represents the density of states times the Fermi function. Okay. So then to sum up then, what we did here is develop these NEGF equations, see, which is in terms of, you have a channel described by H, then you have the sigma 1 and the sigma 1 in, sigma 2 in, that describes the connection to the two contacts. And in terms of these, you can interpret it as these inflow and outflow. And the basic NEGF equations are given here. And of course, in navigating through all these symbols, it helps to keep this analogy in mind, this analogy of the simple semi-classical picture. And one last point is, we have generally been talking about two contacts, sigma 1 and sigma 2. But a very important part of this NEGF formalism, this way of doing it, is it also allows you to include what you might call conceptual contacts. That is, if there is interactions of the electrons with the surroundings in the channel so that it loses momentum or loses spin, etc. Those could be represented also with sigma 0 and sigma 0 n, kind of like these, sigma 1 and sigma 2. And those just have to be added on. Otherwise, the same basic picture would still work. But the one important difference to keep in mind in this context is that when it comes to sigma n, 1 and 2, they are related to this gamma 1 and gamma 2. So what that means is when it comes to the contacts, when you look here, it looks like you got two things, sigma 1 and sigma 1 n. One related to this outflow, the other related to the inflow. But you don't really need to figure out both independently, because if you know sigma 1, you can find out gamma 1, multiply by the Fermi function, and you'd have the n scattering. Same with contact 2. But when it comes to this conceptual contact, the one that represents interactions, there this argument doesn't work, because that contact is not necessarily in equilibrium with anything, because this is a conceptual contact. It just represents this interaction. That is, you view interaction as if the electron went out into some contact and came back in. Right? This is the picture due to Boutiqueur that is widely used. And in fact, in Boutiqueur's model, what you do is model it with a real contact, as if you had 1, 2, and 3. But in the NEGF method, which I consider more powerful and more general, you write it as the sigma 0 and sigma 0 n, but you keep in mind that this is not a contact in the sense there is no Fermi function associated with it. And so you cannot write the in term easily in terms of gamma and f. So I couldn't write sigma in 0 equals gamma 0 f0. So what you can do, that's what we'll discuss I think in the 9th lecture when we talk of dephasing. Main point to note is that for the dephasing contact, this one, you have to ensure that whatever you do to figure out your sigma 0 and sigma, they satisfy this relation. Why? Because at any contact you see, that's the inflow and that's the outflow. In these contacts, this doesn't need to balance that because these are physical contacts where actual current is flowing. So you could have 10 electrons per second come in and 5 leave. But in this conceptual contact, it's floating. Electrons have no place to go. In the sense, there is no real contact there. And so whatever the inflow must exactly balance the outflow. And there is no net current, because if they were unequal, there would be a net current. And the point is there's no place for that net current to be flowing. So that then kind of summarizes what we did here. You see, this idea of a channel described by H and the connection to the contacts, the physical contacts and the conceptual one contact described by these sigmas. And there is this sigma and there's the sigma in, one that represents kind of outflow, the other that represents the inflow. And you can have this picture in your mind of the expression for outflow and inflow. And as I mentioned, very important thing to keep in mind is this Gn is just like the number of electrons, A is like the density of states. And this kind of summarizes the equations we'll need. So what we'll be doing after this in lectures 6 through 9 is applying these to different 1D examples. This would be like the starting points. And in the next unit, unit 3, we'll be looking at more difficult examples. But these basic equations are all right here. Now the next lecture is a bit of a detour in the sense we'll talk about what's called this current operator. That is, here we have focused entirely on charge currents because that's the quantity of primary interest. But these days there's a lot of interest in the current of other entities like spin, for example. And so I'd like to say a few words about a general current operator that allows you to calculate the flow of any quantity. So that's what we'll be doing in the 5th lecture. But after that, we'll be looking at examples that apply these equations. Thank you.